This video will discuss the secant method for solving nonlinear equations. Now, the secant method is an open method for solving nonlinear equations in the form of f of x is equal to 0. It's an open method, so it's similar to Newton's method. And in that sense, it can actually be interpreted as Newton's method, but instead of using the actual derivative of f in the update formula for the solution x, we use an approximate derivative. So instead of drawing tangent lines to our curve in the form of derivatives with the slope of a derivative, we will use secant lines. And what that means will become clear in the next slides. It can be interpreted as like an alternative of Newton's method, but actually a fun fact is that the first application of this method was traced back to this Egyptian mathematical manuscript from 1800 BC, which was 3,000 years before Newton was born, actually. Comparing Newton's method with the secant method will be done using these two graphs on this slide here. So on the left, well, we have both on the left and the right the same function f of x, which we want to solve or find the root of. So we want to find x such that f of x is equal to 0. And in these graphical representations, the true solution is indicated here in yellow. So how does Newton's method work? A quick recap. We start from an initial guess, x1 here. We compute the function at that initial guess. We compute the derivative of the function. And then using this triangle, well, we just say that the new solution will be where this tangent line crosses the x-axis. So that is where the solution in iteration 2 is, and we repeat this process. So again, compute the function, compute the tangent line, and we have a new value for the solution. And we repeat this process, and we see that in this way we can close in on the true solution. Now, in the secant method is very similar, but somehow different in the fact that we do not start from 1, but we have to use actually 2 initial guesses. And what we do is, well, we don't draw the tangent line to the curve, but we draw the line between x1 and x2. And that's what we do here. So this purple line between the function values evaluated at x1 and x2. And then the new solution will be where this line crosses the x-axis. So this will be x3. We evaluate x3, and now we draw the line between the function at x3 and the function at x2. So we draw the line over here, and this will again give us a new value where this crosses the x-axis. So we see that these methods are very similar. And for both methods, we can draw these kinds of triangles, which we base our method on. So we have here this triangle. And here we have a similar one. But the only difference is actually the slope that we use. So this theta that we use in both cases. Now for Newton's method, the slope of this line is equal to the derivative of f at x in iteration I, whereas this is the secant line for the secant method. So here we have the derivative or the actual tangent, and in the secant, well, we have the line between points f at x1 and f of x2. So that's f of xi minus f of xi minus 1 divided by the difference between xi and xi minus 1. So that's the slope of this line connecting these 2 points. The rest is completely similar. So if we know that that is the slope of this line, then we can simply use trigonometry. So again, here we have used geometric reasoning on how to come up with these update formulas. And we see our trusted Newton's update formula over here. And on the right, we have the secant update formula. And the difference is that here we divide by f prime. Here we divide by this difference in f and multiply by the difference in x between the two previous iterations. So in terms of algorithm, this also looks very similar to Newton's method. So we find suitable initial guesses, and here we actually need two. They do not have to be on the same side of the solution, but that's a detail. And while our tolerance is not met, while our stopping criterion is not met, in this case the value of the function larger than a certain tolerance, which we define beforehand, we compute the function in the current solution, and that allows us to compute this secant line. So whereas with Newton we had to compute the function value as well as its derivative, here we just have to compute only this function value, and that allows us to draw the line between the current iteration, the previous iteration, and this line will then give us the new solution in the new iteration. Talking about convergence, well, we already discussed for bisection and Newton's method. So bisection method had linear convergence. The error in iteration I is proportional to the error in iteration I minus 1 with a factor of roughly 1/2. Newton's methods under ideal conditions, this had quadratic convergence, which means that we basically double the amount of significant digits that we have correct in every iteration. There are certain conditions for when this holds, but when it works, it's very fast. Now the secant method has a order of convergence which happens to be the golden ratio, so 1.618. It's between 1 and 2. So it's much better than linear, but not as good as quadratic. The derivation of this is outside of the scope of this video, but it's nice that the golden ratio pops up here though. Let's also apply the secant method to the circle segment problem. So just a brief recap, the circle segment problem where we given the area AS, so this area A sub S, and the radius of the circle, we were to compute the angle theta in this geometric picture. And you can draw f of theta. The solution is between 2 and 3. This is a nonlinear function that you have to then find the zeros of. If you compare this program, which is also provided with the handbook, you see that it's almost identical to Newton's method. The only difference is the update formula. So instead of using the derivative, we use this secant line slope. And that's actually the only difference that we have with Newton's methods. Again, we have to check for convergence and avoid infinite loops. So similar to Newton's method, the secant method is not guaranteed to converge, but it is much more stable than Newton's method. And that's something we will see in a minute. Looking at the numerical performance, well, we already looked at this problem for bisection and Newton, where for these parameters, a stopping criterion of the functional value of 10 minus 4, with these initial guesses for bisection and Newton, we found that Newton converges very fast within 3 iterations. Let's also add secant over there, and we see that the secant function achieves, well, a similar accuracy with only 1 additional iteration. So it's much faster than bisection, but it seems to be a bit slower than Newton in this case. However, we saw that Newton's method really starts to shine when we increase the desired accuracy. So we decrease the pre-specified tolerances that we have on the solution. Where bisection required more than 40 iterations, Newton was able to get to very high precision within only 5 iterations. And looking at the secant method here, well, we see that it only also requires very few amount of iterations, so only 6 iterations are required to get to this very high precision. And looking at the amount of digits we get correct, well, we see that we don't double within each and every iteration as we do for quadratic convergence with Newton, but it's still very, very fast. So this is super linear convergence, and this is also a case where the secant method performs very, very well. We saw that Newton's method was not very robust, so if we were to choose a different initial guess, we saw that Newton's method, the performance really starts to struggle, and sometimes even Newton might diverge, as in this case. Whereas if we use the same conditions for the secant method, um, we see that it converges without any problems. So that's nice. It takes a bit more iteration, so we don't immediately go very close to the true solution. But within 6 iterations, we are able to go to a solution which satisfies the tolerance, and that's really quite nice performance. So it's much more robust than Newton's method, but it's still much faster than the bisection method. Wrapping up on the secant method, it's an open method which does updates based on the current function evaluation in the current iteration as well as the previous one, as this allows us to calculate the slope of this secant line. Different pros and cons. Well, it's quite fast. It's faster than bisection, so it's super linear convergence, and it's much more robust than Newton's method. Also, it's as cheap as the bisection method, so it only requires one extra evaluation of f within each iteration, because you can save the f value in the previous iteration. You can simply save that in memory. So that's again something that pops up when f is particularly expensive to evaluate numerically. This is a handy thing to keep in the back of your mind. The major con is that although it's faster than bisection and more robust than Newton, it's not nearly as fast as Newton. So it's not quadratic. The convergence is not quadratic, which is a slight downside of the secant method.